Welcome to the final lecture. Remember what was the plan originally? In the first lecture, we explained the axioms of quantum mechanics. In the second lecture, we see several ways in which different people interpret these axioms, and we kind of reached the conclusion that none of this interpretation is really satisfactory. Then in the third lecture this morning, we made this exercise. We identify, we said, okay, let's consider a particular kind of experiments and try to construct all the correlations that in any theory in the most general sense can produce, because we want to compare that with what we have in quantum mechanics and use that to identify what are the principles that shape quantum mechanics. But then we found that the set we got is identical to the one in quantum mechanics. And then we start making some narrative and saying, well, this is the plenitude principle that previously appeared in particle physics but acting here. Simply, this means that a restriction means, in this language, a law of nature, saying you cannot go beyond this point because you are violating something. However, here, effectively, you don't have anything like this. There are no laws. This is really the signature of the fact that you get all the correlations, not just a larger than classical set of them, but actually all. This last lecture, we will try to feel what is missing, try to answer how this may solve the interpretational problems we present in the second lecture. We have 3 tasks. Okay. This is the conclusion, and in the third lecture, this set of correlations is explained by the principle of plenitude. All possibilities are actual occurrence. This is exactly the reason why it's much more than objective randomness. We really need, the only possible solution is to assume the total absence of restrictions. This absence is ontological. This is what we said. But then I will add something at the end to connect this with the ontological problems. It might be the case that forcing the nature to produce these answers or getting these probability distributions might require a specific type of experiment, specific in some sense to be defined. And it would be nice to identify what is specific about these experiments. So, now yes, we have 3 purposes today. The first is a Spiritism session. Together, we will try to visualize what the ontological absence of restrictions mean. And we will do the following. First, together, we put a lot of effort in visualizing an experiment for which we understand why we get a particular outcome. The moment we all agree that we understand why this particular outcome is happening in this particular experiment, then we take our hands together and try, and then I would say, at this moment, everybody please do this, okay? And check whether it works or not. So this is the plan. It's not science, I know, but it's a nice experiment. Then I tried to connect things and explain. I tried to identify what is special about a quantum measurement. Because, I mean, it took a lot of time to find experiments in which all this behavior is happening. It's taking a lot of time to really produce machines, quantum computers that really behave this way. It's very expensive. We have to pay attention to many details. Why? I mean, what is special about all these machines? How? And this is what I try to identify. And then, when we have completed the two previous steps, like getting a picture of what's going on and identifying what is special about the experiments in which we produce this interesting non-classicality, then and only then I tried to say, well, in what sense this solves or make progress into the interpretation of quantum mechanics. So first we have to find an experiment that all of us understand. It has to be an experiment like the experiments we've been using all the time, involving a preparation and a measurement, as we explained in lecture 1. And then, as in quantum mechanics, we should be able, in these experiments, to classify preparations and measurements into a class of equivalents. Each of them will be a state in the case of preparations. Each of them will be an observable in case of measurements. So we are not cheating. We really can use exactly the same language for the experiment. And moreover, we have to really know, understand how we can prepare every state, how we can measure any observable. And then, and that's the hard part, we have to convince collectively that we really understand why a particular outcome is generated in that experiment. That's the task. So one good thing about the internet is that you discover that there are many people interested in cheating. So there are a lot of sites in which you learn how to weight dice in essentially, and that's my point, any way you want. You can use additional weights, you can use magnetic fields, you can put magnets in the die, you can put magnets in the table, you can combine them. And this is exactly what we need. Because I think this is the experiment I'm proposing, is rolling a die on a table. The measurement is the act of rolling the die, and then the outcome is going to be which face is up after rolling the die. Okay? Possible results, we agree. We agree that, well, typically when we buy dice, we assume that these dice are fair, meaning this, equal probability for each of the faces. But the purpose of the first transparency is to convince that there are people that are really good and they can really manufacture a die such that you always get a 5 when you throw it. Do you believe that? They can do even better. They can manufacture a die such that you get a 5 with probability 1/2 and a 4 with probability 1/2. Right? Why not? And in principle, you can manufacture a die, you can prepare a die Anyway, the only condition is that the sum of the 6 probabilities has to be 1. Okay? There are different ways to prepare the same state, but we said it's the same state, it's the language we use. There are infinite states, but there are only 6 of them that are, cannot be expressed as convex combinations of the other infinite ones, namely the 6 obvious pure states. It's the same language and in quantum mechanics. I don't know why we don't teach quantum mechanics this way. Observables. How many observables do we have here? 52. Okay. Why 52? Because you have potentially 6 outcomes and there are 52 ways to partition a set of 6 outcomes. So for instance, you have the observable, is it odd, which corresponds to a partition in which one partition is 1, 3, 5 and the other is 2, 4, 6. You have the 2 outcome observable, is it smaller than 4, which is again a partition into different partition. 1, 2, 3 versus 4, 5, 6. Then there's also an observable that is the one outcome observable. Is it a number? It always has the same outcome. Yes. Okay, but it corresponds to one partition. And then you have the 6 outcome observable. Which number is it? So do we agree that we are talking about something very similar than in all the experiments we talk? We have preparations, measurements, and then we can define states, and then we can define observables as well. Yeah, different ways to measure the same observables. Okay. And then that's special. The last one is special because by measuring this last one, we measure the 52 observables at the same time. Okay, so all of them are jointly measurable in this case. But now we have to really sit here and discuss a little bit whether we understand how, when I roll the die, I get a 5. And I suggest you to think that classical physics provides a way of understanding this experiment. So we model the die as a rigid cube with a specific size and weight density. Okay. Then it's true that typically when we roll the die, the purpose of rolling the die is not to watch anything. So you roll the die without intentionally watching the condition, you throw it on the table. But if we could know the exact initial and boundary conditions, the orientation, the velocity, the position of the center of gravity, the force with which we throw the die, the torque, the resistance between the die and the surface, the air resistance, then the laws of classical mechanics can be used to exactly predict with certainty that the outcome is going to be 5, a fraction of a second before we actually get a 5. That's a way of understanding. Feynman said he understands when he can tell the layman something. Well, I'm just pointing out that in all the teaching in classical mechanics, we do this, we assume this. And this is the way we've been understanding classical mechanics for 200 years. Is it a valid way of understanding that we get a 5? You can visualize it? Albert, you're not.
Well, hardly.
Half of it. What else you need? I mean, what part you don't visualize?
Well, the difference between loading the dice and not loading the dice.
Ah.
I see that there is a difference.
There's a difference, yes.
But which kind of question are you asking me?
Okay, now I was asking whether you are satisfied as this explanation as this is a way of understanding. We can claim that there's a sense in which we understand why we get exactly a 5. In this particular case, we've always said, okay, the 5 happens because the initial condition was there, we have this, and therefore, because of these laws that are basically conservation laws, has to be a 5. And in practice, we can apply all this method, and really fractions, we can, at this point in the movie, I know that it's going to be a 5. And we can check that and work. So it's understanding. Why it's happening here? Why we get a 5? What requires getting a 5? Let me point something obvious. Nature doesn't have die. A die is a human construction, is there for thousands of years. Okay? But in this experiment, why? I mean, and we define the whole thing, that's true, but why actually we find an outcome? Mainly because there's one intrinsic property of this object, namely it has 6 faces. And when I said it has, I mean this object has these 6 faces at the beginning of the experiment, during all the experiment, and at the end of the experiment. And this is crucial because, in particular, it tells you that the possible outcomes, the set of possible results, is either 1, 2, 3, 4, 5, or 6. This intrinsic property defines the set of possible outcomes. But there are other intrinsic properties that are preserved through the whole experiment and play a role in the final outcome. For instance, the mass, the exact volume, the distribution of masses. The distribution of masses is clear, but it's intrinsic. Whatever distribution it does not change during the whole process, and matters. Okay. But matters is what I'm trying to point out in a slightly different way, that the fact that you have 6 faces matters. The fact that you have 6 faces tells you the set of possible outcomes. Well, the distribution of masses matters in the sense that determines a little bit whether it's going to be a 5 or something else. And there are other intrinsic properties that are more or less irrelevant for the experiment. For this experiment, for instance, the color of the die. We don't think it makes a big difference, but they are there. So we have intrinsic properties, but in 3 different roles. Some of them define the set of possible outcomes. Some of them are important in the generation of the actual outcome, and some of them are irrelevant for anything of this. Got it? We agree? The generation of a result requires the preservation in time of some intrinsic properties. But these intrinsic properties play different roles. The specific result depends on variables: orientation, velocity, position of the center of gravity, force, torque, resistance between the die and the surface, air resistance, that might be hidden to the experimenter. But these intrinsic properties are the ones that determine a particular outcome, that restrict the possible outcomes, determine this, guide the actual outcome. Summing up, take-out message. In this experiment that we think we understand perfectly, a result occurs because of the preservation in time of certain intrinsic properties. However, they play different roles. The set of possible outcomes is dictated by the preservation in time of some intrinsic properties, the number of phases. The final outcome depends on additional, possibly hidden, intrinsic properties or variables that follow physical law, restriction law. We understand everything. Good. It was easier than I thought. Okay. Now let's try to understand a quantum experiment. Why the outcome of a quantum experiment occurs. Oh, sorry. We cannot. We are not even allowed to ask the question, how can it be like that? Because Richard Feynman said, don't try. Because why is it people try and fail? So be totally aware that you are doing something illegal. Okay? What if a result of these experiments occurs because the preservation in time of intrinsic properties? I don't mean the specific outcome, but the fact that you have to have a result. It happens because there are properties that are preserved in time. So, and because of that, you have to have a result. There's no other way out. What if, in addition, there are intrinsic properties preserved in time that dictate the set of possible outcomes? Has to be 6 outcomes, has to be 2 outcomes, or 3 outcomes. But what if there's a difference with the previous case, but only one difference? You designed the experiment so the experiment enforced the occurrence of an outcome which is not an intrinsic property and does not depend on hidden variables. Can you visualize it? Good. That's the right answer. Let's build an image in your mind. This is a Sterke-Lach experiment. We presented the first lecture. Let me remind you that here you have a source of silver atoms. Has to be silver. Then you have a slit. Then you have a magnet with a specific gradient, specific length. And here you have a glass plate. And what you see at the end of the experiment is simply an accumulation here of silver atoms. And there are 2 possible outcomes, either up, either the atom accumulates in the upper or in the lower. Okay. This is the experiment we want to visualize together in this session of illegal spiritism. Okay? Our results, meaning one particular spot in one particular position in the plate, occurs mainly because the preservation in time of intrinsic properties. You have 47 electrons. Whatever it is, whatever the shape it is, you can count them, right? There are 47. So, and there are 47 at the beginning of the experiment, there are 47 at the end of the experiment. And there are 47 protons, which are even bigger, whatever it means. They have larger mass. And at the beginning of the experiment, at the end of the experiment, and in addition, you have 60 or 62 isotopes, neutrons, depending on the isotope of silver you use in the experiment. Actually, probably they use 50-50, because it's what you get in nature for free. But what is preserved between the beginning and the end is the mass, the charge, electric charge, the total spin. Has to be preserved. You have to have whatever answer, a spot, because the silver atom cannot vanish. But then there's an intrinsic property that in quantum physics we call the total spin that tells you in this particular case that the possible set of outcomes is just 2. It tells you it has to be 2. And this 2 is detected by the intrinsic old-fashioned classical property. But the design, and by the design I mean this complicated interaction between this very specific atom and this very specific magnetic field for this very specific length, is very designed, enforce the occurrence of a variable ending into an outcome resulting from what? The interaction between what we call the spin component along the direction of the axis of the inhomogeneous magnetic field of the Stergalach magnet and the magnetic field itself. This enforces that. But what if the actual outcome, up and down, is not related to intrinsic properties or hidden variables? Better? Can you visualize now? Better? I'm just saying better than before? Good. Now I'm happy. I'm happy. I will celebrate and tell you the rest of the story because I never saw this convincing reaction. Now I'm super happy, really. So, okay. Then we have, in this conclusion, I added for this particular talk, this maybe revealing this particular ontology may require a specific type of experiment. In the case of a Stergalach, if you change silver by palladium, you don't get that. If you change the magnetic field, you don't get that. It's really a lot of work behind that experiment. You really have to nail it to really get this split. They got a Nobel Prize for. But it's just saying that it's complicated. But by specific now, I would like to identify what is really specific and common to every experiment in which I manage to produce outcomes that manage to saturate the predictions of quantum mechanics. Okay? What is special about these experiments? This is connected to one of the open problems. What is a measurement device? What is a quantum system? And we've been working on that, Matthias Kleiman and myself, for quite a while. Matthias Kleiman. And we reached a very surprising conclusion, unexpected conclusion, totally different than what you heard. Carlo Rovelli said, any device is a measuring device. A tree can be a measuring device. We found the opposite, quite opposite. No. To get this, you really first need 3 specific ingredients that we call the measure system. Everybody understands that, thinks to understand that. But we never measure on the measured system. Never, never, never. In any of these experiments, we never do that. That's the first, what? Never. What we do, we identify a second system that we call it the pointer. We also need something fundamental that we start talking, referring to it in a previous paper as the principal measurement. But this is just ingredients. Actually, we need to combine this ingredient in a very particular way, and the measurement itself is a sequence of 3 well-defined phases that we call interaction, detection, and update. I guess this is the most interesting slide. This is what we feel, and we couldn't find any counterexample of that, is common to all the experiments in the planet in which you get quantum outcomes. You first have your system, the system you want to measure, okay? And then you need to identify another system, the pointer, and then you identify a feasible interaction between these two that you applied during certain time, and then you have to identify here the principal measurement that actually is measuring the pointer for a while, and is very specific machine, because here, by definition of principal measurement, the outcome of this thing has to be something that you can copy. And there's a final update, and when somebody, after copying this, reads some of the copies and says, oh, it was a 0. Ah, this means. But in this phase, if you somehow look at the target, nothing happened to the target. This is originally intended to explain Roger Penrose why there's no conflict at all between the double evolution and quantum mechanics. The conflict for Roger Penrose is that you have a unitary evolution if you don't measure, but there's a collapse, a jump, instantaneous, when you perform a measurement. He insists a measurement is a physical process, and he's totally right. It's a physical process that takes time. You can play with the time. In that sense, he's totally right. But we don't see any conflict, because our claim is that the evolution in this phase is totally described by unitary evolution. In this phase, is essentially described by a unitary evolution on a larger system. It's Lindbladian, but you can really, and that's the goal, you can really test whether it's compatible with a unitary evolution. And in this phase, the system is not evolving at all. There's a person reading a paper and then making a classical Bayesian update of the previous catalog of probabilities he had before. You don't need many universes. You don't need spontaneous collapse models. It works. And then he said, the really scary thing is that if you go to particular examples, you identify these ingredients. He said, oh, in the circular, well, the target is what we call Z component of electronic spin. But you need a magnetic interaction between this thing. And then the pointer is actually the atom center of mass. And what is the principal measurement? Well, there's a moment in which you have a deposit of silver atoms. It is there. You can copy. In a trapped ion, you have the electronic levels of the ion. This is what you want to measure. But actually, you don't measure that. You have an interaction with fluorescence. The pointer is the magnetic field. And you put here a photodetector, which is a machine that takes a magnetic field and does a super complicated thing, creates a super powerful electric current that you interpret as 0 or 1, and so on. This is not what is taught in most places. So this kind of completes the picture of what's going on. Now the question is, to what extent everything I told you solve or advance the interpretational problems of quantum theory? I will present some senses in which I think this helps a lot, but there are too many senses. We can keep discussing after that. The first one is my main question. Where does quantum mechanics come from? Actually, John Wheeler's question. What deeper principle does quantum mechanics arise from? Why quantum mechanics works? What property of nature produces phenomena that cannot be explained with classical physics, but is well accounted by quantum mechanics? And the answer is the one we got in the previous lecture. The absence of restrictions that makes every possible correlation obligatory. The most common misconception is that quantum mechanics is kind of in conflict with reality, with the existence of a reality out there. I have to disagree. It's the opposite. To really produce these outcomes, these numbers, you need reality. It's mandatory. You need the 47 electrons, 47 protons, 62 neutrons, their mass, charge, total spin, to really get a spot, to really get a 0 or a 1. It's mandatory to define the whole thing. Reality is there. If you are worried, if you call reality, oh, it's a 0, that, well, what is reality is that there's something that was there at the beginning is now there in the screen. That's real. Is everything quantum? I would say most of the community, Albert said yes, potentially yes, but I tend to disagree, not because for really well-defined reasons. Apparently, the experiments covered by quantum mechanics, that is true. Remember the first lecture. They do happen in an extremely wide range of scales using extremely wide variety of systems, but all of them seems to require these 3 ingredients, 3 phases. And in some cases, you see natural situations in which they happen. But most of the cases, we have to engineer the things to make these things happening. Okay? And in a clear mathematical sense, this set of interactions is just a subset of the possible interactions. Quantum mechanics describes perfectly these interactions and everything that can be traced from these interactions. But isn't clear that all interactions are like this, or in a sense it's clear that there are some that are not like this. Probably there are physics beyond quantum physics. Where is the cut? Remember the discussion in the... Well, Niels Bohr was more correct than Werner Heisenberg in asserting that the cut is determined by the experimental setup. Remember that Heisenberg said, no, it's a mental construction and it's totally flexible. However, Niels Bohr was not quite right, because the cut is not a cut between the quantum observed system and a classical measuring apparatus, but to be more precise, the cut is between the input, whatever it is, and the output of what we call a principal measurement. So in every experiment, where is the cut? Identify the principal measurement, exactly, the input of the principal measurement, the output of the principal measurement, the cut is somewhere in between. But not after that. Okay. What I'm saying, in the Schrödinger cut experiment, the cut is not after the cut. It's way, way, way before the cut. Schrödinger's cut. Meow. Right? And what about the measurement problem, this double evolution? What about the meaning of the wave function of that? Mermin, remember that I used David Mermin in the second lecture, is essentially right about this. There is no quantum measurement problem. The entire content of what we call the quantum state is a catalog of probabilities. Remember how we did it, how we defined the state. Really do some operations and say, okay, what is common to this and this is this. This defines a state. The acquisition of further information can lead to an abrupt change in this catalog. The moment you have new information that now the table has changed, you have to change your catalog. This is what you do. It's abrupt. Well, it takes the time for you to read the outcome and to make the correction in the catalog. However, that's true. Penrose was correct to point out that the measurement is a physical process, but it is a very specific physical process. And with this, I have to really thank you for coming. It's been a pleasure to be here. Thank you for your attention. Thank you for the invitation. It's been really a pleasure.
Okay, thank you very much. It's time for questions.
Which opinion do you prefer? Wheeler's or Mermin? David Mermin or the other one? You say that both are
Lovely. Okay. That's an easy question.
Maybe you are
No.
change your mind whenever you want.
No. It's, John Wheeler was really the person that I think had the best vision of there's a solution, it's simple, it's there, we have to work. He was obsessed by this hypothetical vision, is that he was a friend of Einstein, he was under the supervision of Niels Bohr. So he was perfectly aware that both of them were really bright people. And it makes him mad, the fact that they cannot agree. And he was obsessed by the idea there should be a way to explain Einstein why Niels Bohr is right. Actually, the same way to explain Bohr why he's right, in a sense. So he started that, but he died without having the final thing. And you can have a beautiful interview in the in the web of science in which Wheeler talks for hours about the problems, the motivation, and so on. And he puts this thing in many of his students, and this has propagated in time, and some of the progress is due to this obsession. This was really an obsession by John Wheeler. The case of David Mermin is completely different, because David Mermin is among the very few famous physicists that have been changing his mind in time. He started not really worrying about that, but then I realized you have to worry about that. And around 1998, he found the solution. He called it the Ithaca interpretation of quantum mechanics. And in the usual way, he wrote a beautiful paper. Beautiful, beautiful paper about that. So beautiful that our common friend, my supervisor, was in love with that paper. This has to be the solution. Essentially, the idea is that quantum mechanics is not a theory about outcomes, but about correlations. So the fundamental object is correlation, and it's about how these correlations are changing in that. Again, very beautiful, but wrong. In the sense that we publish a series of papers explaining why it's wrong. It's just moving the garbage somewhere else. Instead of calling element of reality the outcome, you call element of reality the correlation. But you use exactly the same machinery of no-go theorems in quantum mechanics, and you kill that. And David Mermin recognizes that he was wrong. He put it in written, and he said, after reading the paper of this guy, and that guy, I realized that it's wrong. And then I spent a lot of time thinking alone. And then one day in Stellenbosch in South Africa, knocked the door of Chris Fuchs and said, you are right. And embrace cubism. But immediately kind of departed a little bit from Chris Fuchs. So he has his own vision of cubism. And then, as I said, or tried to say it in the second lecture, cubism is, what I feel cubism is the only way to really make sense the moment you assume that you can and you should apply quantum theory to everything. If you really think everything is quantum and follow this rule, and every decision in life has to be based on applying Hilbert space formalism, and you believe this includes Wigner's friend in particular, then cubism is not as crazy as people said. Actually, it's kind of mathematically. But the question is whether you have to do that in this universe. And this is what I try to say, you don't need to that, because quantum mechanics works here, here, and here for this, and this reason, but it's not the universal way of thinking for everything. And therefore, hopefully, David Mermin will change his mind again. I don't know.
Questions?
Yes. I can ask. So now that you have solved the measurement, or we have solved, you have solved the measurement problem?
We have solved this. You have solved the measurement problem. But only you realize this on Monday, Wednesday, and Friday. The rest of the days you still doubt it, but you solved it. You solved this measurement problem. Yeah.
So quantum mechanics is solved, or is it like still things that need to be fixed or things that need to be understood?
Quantum probability theory is I think I have a compelling view that why it works, what does it mean that it works. But I don't understand why the Planck constant has the value it has, why the electrons have the values. I don't have any idea why the 19 parameters in the standard models have this value. I don't really know where is gravity here. I don't know. There's many things to do.
But a different type of question, or is it the same type of question? You just don't understand how to ask it.
It's a different type of approach to the same type of question, in the sense, if you are trying to design experiments to eventually convince people that the gravitational field is similar to the quantum fields we have in the standard model, then this approach, your approach to how to design a compelling evidence, is valuable. So now it gives a detail on how to design experiments, presumably providing evidence of so-called quantum gravity. It's a way of making progress. Because if you think that a tree can be a valid measurement device, and you are doing at the same time quantum loop gravity, you have a problem. Or if you do cosmology and you are Bohmian, you have a problem as well. And you somehow convinced that there's a better explanation, simpler, and there's a way to make faster progress and stop arguing about things and using formulations that have been used for 100 years and have consumed tons of energy and still consume tons of energy. We use our energy to explain why many worlds, why don't many worlds, why spooky actions at a distance, why don't spooky actions at a distance, without using this energy to really make progress. And I hope this helps to avoid this discussion in the future. So eventually, if nature conducts a survey in, let's be optimistic, 10 years, then there are more agreement on what is this thing called quantum theory about. And then we can really have more communication, more fruitful communication. Yeah.
Okay.
Three things again for results. So you said at the end that when you measure, you update the catalog. Okay. So this is something from the person that measures the system, knowledge, let's say. So the reality which is behind this silver atom has changed somehow, or?
I changed the place. It's moved from the oven and to the screen because you force it to move that way. You create all this design. But at some point, I've moved up or down. But this is, in that sense, now you can really use the poetry people use is a really act of creation. But what you create is, no, I mean, you have to finish up or down. But you have to finish. You designed something that forced this to finish. And there's a little creation, but it's not the whole reality, is my point. There's something that is created, classical information, but the cost is, okay, what is needed to create that is reality preservation and more things. But now, regarding the update, what is meaning the changes, I mean, because you can use this information to update. Remember that the update is right at the beginning. When we construct these boxes, we play a lot of games, and then we create a table and said, oh, this table with this catalog is called state A. Update, you have to update because basically now when you do the measurement, suddenly you have extra information. So you have to update, you have to add this extra information. So effectively this table changes. And following the same rule, you have to call it differently. But it's what you create, what you used to make predictions is your own set of rules. You are simply following your own set of rules. Then you have to update, or you can do, okay, I have this information, but I prefer not to look at it. Well, yeah, let's look at it. So it's up to you. But as a point, we claim that during this update, this collapse, you can monitorize the whole system and notice that nothing happened. Actually, we have this discussion, how to convince people, I mean, what do you have to measure to convince that nothing is happening? Here. I said, whatever, but we have to convince because it's precisely where people expect a jump or something strange and actually it's super boring. Okay? But it's this under the assumption that the model we have really matches with the experiments. We don't know yet. We have to do the experiments. We have to. Okay? The theory matches, but maybe nature fails or the experiments are not good enough to really confirm this thing.
Okay. More questions?
Young questions? Okay, don't take it personally. Don't take it personally. Younger. I said younger questions.
And what about when you have entanglement?
What about?
Entanglement.
Oh, entanglement is a beautiful name that we create to, when we say correlations, these tables are just, to create these tables you need a mathematical description of a vector or a density matrix and a mathematical description of the observables. And then imagine as a pure state, therefore the mathematical is a unit vector. One day, someone wake up and said, oh, this mathematical object cannot be split in terms of product of these two things. Oh, that's super nice, that's super important. Let's put a name in that, say this is the characteristic trait of quantum mechanics. Entanglement is one of the possibilities. It's related to actually many of the possibilities. You need entangled state and incompatible measurements to really violate the Bell inequality. But it's there. It's simply you fill the bottle and said, oh, there should be, because of this argument, this table should exist. By the way, I've been using a table all the time that requires a very specific entangled state and very specific measurement that is super important. But then I said, according to this thing, this table exists. Therefore, in this description, this vector has to be this one, this observable has to be this one, or rotations of that. And then we make this mathematical observation that to get this beauty, there's a kind of connection, but it's not one-to-one, it's a bit more sophisticated between the cases in which the vectors cannot be represented as product vectors and the fact that you managed to violate the Bell inequality. But then you use entanglement over and over as entanglement was something there, but it's simply a mathematical consequence of the whole thing. Right? You can prove, you can sit. Remember the logic. We get this, the bottles, this, the tables, and then we said, well, but the tables is the theta body. And we say that what is the theta body? Theta body means that these probabilities should be expressed as a vector and then that. And then, oh, if it's true, now let's examine the points that are interesting in this Bell experiment from this language. And there is when you find the entanglement. To get a point outside, one property, if the state is pure, is that it has to be entangled. And then you make a lot of papers about that. And then you spread the idea of that entanglement is where the magic is. And then everyone talks about entanglement. But yeah, I don't know about nature talks about entanglement. Nature talks, period.
One question more.
Yep.
Regarding the dice introduction you made, first you introduced us on the idea of Laplace demon, and after you make like a second part about non-intrinsic properties of the dice that define the result.
Not of the dice, not intrinsic properties, period, in the sense that I said the interaction between, in the Star-Gelac case, the interaction between that thing we call atom and that thing we call magnetic field, or more precise, this property we call spin component, blah, 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 sort of enforce a variable that at the end of the day becomes an outcome. And this variable is not guided, is not determined either by intrinsic properties, and by that I mean intrinsic properties of the die, or of the table, or of the magnet, or of the silver atom. I mean, this lack of determination, this is the key thing. The logic is like this. By design, there has to be an experiment. I always put the same example. A football match. A football match, by design, can have three outcomes. Team A wins, Team B wins, even. By design. And now the question is, what determines any possible particular outcome? And the real life is many, many, many hidden variables. Okay? If you know that Team A, all of them are sick, you have an explanation of why Team B is winning. The reason why this exercise of visualizing is because visualizing absence is very complicated. You have to have something and then suddenly make it disappear. That's why I put the example of the die. In the die, you see the variables. Air, pressure are there. All of them are there. And the moment there are hidden variables, there's no chance of non-classicality, let's say. But then there are a wide variety in which you may, this lack of hidden variables can be manifested. You can have a partial lack, or you can have, like here, we're saying, the only way to understand why we, in the experiments, we manage to really reach every point is that collectively, in these experiments, there are no hidden variables of any type. In the system, we are supposedly measuring. In the device, we are supposedly using in the interaction. There's nothing. That's absolutely nothing. The moment we put restrictions, it means that we cut parts of the set, so there are areas that are impossible to access. And that's probably part of the problem why quantum experiments are difficult, because noise means really having things you can trace, and then you cannot reach certain possibilities.
But, like, I get what you're saying, but my question was more about having this in consideration, theoretical Laplace demon in a quantum field could never know what number will result. There's no actual available properties that can give us an answer.
If the demon has access to the present, no. If the demon has some mechanism to read the outcome and back in time, maybe. But I don't think this mechanism exists. So it's like you can change the word demon, Laplace demon, by God. And that's God knowing everything cannot exist, or if exists, should know absolutely everything. And then we kind of have this problem of fine-tuning we mentioned regarding superdeterminism in lecture 2. So essentially, there are just two ways to be consistent without jumping into retrocausal issues. And one is assuming that, well, there's these areas, these experiments in which there's nothing, even God, Laplace demon, the best scientist in the planet, can get in advance the answer, the outcome, or if you are not care about the cost, there's someone who knows everything, essentially. Thank you.
One more question. Participative universe of Wheeler is related to the process of measurement. Participative.
What do you understand by participative universe? Because there are two ways to understand, and I guess the standard one is saying we create reality when we measure. And part of my point is, not really reality. We use mainly reality preservation to create zeros and ones. We said, okay, the fact that it's 0 and 1 translates into the fact that the atom has accumulated here. Well, the atom should accumulate it in any, but why here in this space position? That's reality. Is that reality? Because I really don't know. I mean, it's an honest question. What do you mean by a participatory? It's also beautiful. We create reality. Okay, that's good. Super powerful. You feel better. You are creating reality every time we go to the lab. You are creating zeros and ones. And the same in a quantum computer. I don't feel we run the quantum computer and you end up having sequences of zeros and ones. Do we create reality by doing that? Do we? I don't know. I mean, yeah, in a sense, we create zeros and ones that weren't there before and we can use them. But is the whole universe like this? The it from bit from John Wheeler, is every reality produced that way? John Wheeler tends to believe that this is the case, also a higher energy, so eventually, but I don't see evidence of that. I still see this boring classical view that we have reality and then sometimes you don't have laws and then you have this particular sequence of zeros and ones. So far is all the beautiful things I see. Then maybe there are missing important things, but this explanation is fair enough so far.
So maybe it helps if you define reality to be copyable information, then it's maybe easier to find something unreal, otherwise reality is a very...
Then we create reality.
Will make quantum, we don't know what's
If reality is something you can copy, sequence of zeros and ones, and yeah, do we create reality when we write books? Because people have been writing books forever, and I never heard them saying we are creating reality. Although in a way they are doing in a very similar way that the reality created by a quantum experiment, quantum computer. So if reality is a sequence of zeros and ones that wasn't there by using ink, pre-existent reality, you use the ink to write the book. You force the ink to be in the paper. The ink doesn't have any option to be in the paper. Okay, but this is kind of different because apparently the ink has an option to be 0 or 1. It's a different reality. Got it? Yes, I agree. If this is reality, yes, we are creating reality every time we conduct one of these experiments. If you feel better, fine.
Well, thank you very much for the fantastic lecture today and yesterday as well. And since I'm more confused than when I started using for the whole journey, I want to say, talking about reality, but in my field, the master, well, I call the boss, is Salvador Dalí for me, that said that the existence of reality is the most mysterious, sublime, and surreal thing that can be discovered.
Look, this is my answer. Yeah, it's part of what Matthias mentioned, what is left. I really don't know. I think physics has something to say about it, but not me. Yeah.
You develop the eat from meat from Miller.
Who?
The idea that eat from meat.
The idea of eat from beat represented typically is a universe that is self-observing, as it's self-creating. It's a beautiful metaphor. It's very Wheeler. I mean, Wheeler was a very strange person. Personally, politically, was super conservative. Intellectually, was wild as no one else. Just, and then he has this view that the universe is self-creating itself by observing. So the universe is a constant act of creation. So sort of suggesting that, yes, zeros and ones are real, and their parts are bricks in the universe themselves, and then organize, and then watch another parts of the universe, then create extra reality. And reality is growing that way. It's super beautiful. It's another poet, right? But I mean, you face me with Dalí, Wheeler. Come on. I mean, I wish I had conversations with Wheeler. I mean, at night I put Wheeler, said, just to hear him, said, because this is an inspiring person. It's really beautiful. But it was, yeah, he had all kind of strange ideas. It's how he made progress, trying everything. How far to go. Many worlds comes from Wheeler's student. One day, because Wheeler typically put the exercise, typical exercise, Wheeler, this is true. It's for tomorrow, homework, take notes, derive quantum mechanics. See you tomorrow. You cannot do it better. That was Wheeler. So, yeah, I don't know.
Okay. So, we finish? Okay.
So, big applause, no?
Sí, sí, sí.
It is now time to conclude these lectures. These lectures have been a great opportunity to listen to one of the leading specialists in the foundations of quantum physics. Professor Adán Cabello has not only shared knowledge with us, but also a way of approaching the most difficult questions with rigor, humility, and passion. These 4 lectures have reminded us that quantum theory remains a living, surprising field, full of essential questions. Adán has shown us how foundational research is an area that can shape the future of physics. Thank you, Adán, for sharing your knowledge and your vision with us. And we would like to thank the Faculty Moral Chair, especially his director, Joan Vergés, and his secretary, Ramon Fàbrega, for all their work in organizing these lectures. Today they are in Barcelona because they organize a symposium in Barcelona. Thank you as well to all of you for being with us here. Okay, thank you very much.